Welcome Year 9 to this next video. I've decided to make this video because I think we needed to have a look at some of the trickier examples that we might come across in this topic. And one of the things that we really need to look at is some of the angle facts that we started looking at last year, possibly even in Year 7, but mostly in Year 8 we looked at some angle facts, and we really need those for this topic as well. So the couple of examples that I'm going to go through first, they're going to draw upon that knowledge. Okay, so what we're doing first is having a look at this example here. We're asked to prove that these two triangles here are similar. Now, as we can see, one triangle is larger than the other triangle. We can also see that they are not sitting in the same orientation, are they? Some of the examples we've looked at have been a little bit easier because the triangles are sitting the same way up, but these ones are not. So it's going to make it a little trickier. We want to prove that they're similar, then we want to find this value here, the value of x. Okay, so let's get started then. What I'm going to do is just examine what information I've got. I need to prove that they're similar, so I need to use one of the tests. So I could use AAA, SAS, SSS, or RHS. So as you can see, we've got two sides shown on this triangle, and we've got one side shown on that side. So I don't have here, I don't have an SAS proof, because as you can see, this side here, the x, it's not shown. So I couldn't show that the ratio of two sides was the same if I don't have that side there. So what else could I do? Well, obviously I can't then do SSS, there's not enough sides. I can't do RHS because there's no right angle. Not that I know of, at least. It doesn't look like there is. So what I'm going to have to do is examine possibly, can I get the AAA test? Well, I've obviously got this one here, the 30 degrees. And you're probably looking at this and going, well, I don't have any other angles. But I actually do. This one here and this one here. These are, in fact, the same angle. The reason that they're the same, we say that they're vertically opposite. So hopefully when I say that, you can remember that from last year. When you've got these angles like this, you've got two straight lines that they form sort of like a cross, I guess. These two angles here, they are vertically opposite. They are the same angle, exactly the same angle. So therefore, what I have here is a 30 degrees and this angle here that's the same as this 30 degrees and that angle there. So I have two angles that are the same, and of course once we know we've got two, we have the third due to the sum being 180 degrees. Now that I've established I do have similar triangles, let's prove that they are similar. What I'm going to do first is say that angle DEC, so that's this one down here, is equal to angle ABC. So I've matched up the vertices as I've said this. Now that angle is 30 degrees. Now I want to make a statement that's saying that these two angles here are the same. So I'm going to say angle DCE is equal to angle ACB. And in brackets I'll put my reason, they are vertically opposite. Now that I've established I've got two angles, the third must be the same, so I'm going to go straight through to my similarity statement now. Triangle ABC is similar to triangle DEC. So to match up here, because they're not sitting the same way up, I go A is the angle that has not been shown. It's not there. A to B, where the 30 degree angle is, to C, where that vertically opposite angle is. That is the same as D, that's where the angle is not shown, E, where the 30 degree angle is shown, C, where the vertically opposite angle is. So these all match up. What's my reason again? It's the AAA test. So that goes in the bracket. Okay, I've proved now that they are similar, so I will write out my workings just like this explaining in each step parts of this proof here, either the A, or perhaps it would be SAS even if it was a different example. Now what I'm going to do is find the value of x, this one here. So I want to set up the ratio, because I know that now that they're similar, that the sides will be in the same ratio, the matching sides will be in the same ratio. So what I'm going to do is look at this side here, the 8, and find what side does that correspond to on the smaller triangle. Have a look at the angles that are on either end of that side. I've got here the green angle and the blue angle. I've color coded it. So I've got the 30-degree one and the vertically opposite. And as you can see, this side here, CE, that also has those two angles on either side. So what this means is this side over 6 must be equal to the ratio of the other two sides shown. So I've got the 12 here, and I've got x, don't I? So this must be equal to 12 over x. There we go. Alright, what we want to do now is finish this off. What we can do is multiply both sides by 6. So let's do that now. That means 8 would be equal to 72 over x. And then finally, x must be equal to, oh, I've run out of space here, 72 over 8. And what's that equal to? So, x must be equal to 9 in this case. So what I've done here is just set up these. This is our ratio. We've called this, as we've been going through this unit, the scale factor, haven't we? So what I've done is I've said that both of these, this is the scale factor 8 over 6, that's got to be equal to 12 over x. Now some of you might simplify this here to 4 over 3. So you might have instead 4 over 3 equals 12 over x. You could also solve it this way. Multiply both sides by 3. That would mean 4 equals 36 on x, and therefore x equals 36 on 4, which is 9 as well. So both of those are valid ways of working it out. Just make sure that you've got your matching sides, please. That's really, really important. The 8 here corresponds to the 6. The 12 corresponds to the x. Okay, let's have a look at another example here. This example says, prove that the two triangles shown are similar. So we don't have anything, any x value to find or anything like that, but we do have here two triangles. We can see there's a smaller one here, and then we've got our larger one there. Okay, so let's have a go at this. What have we got? Well, in this smaller triangle here, I've got an angle and a side, and in the larger triangle here, I've got an angle and I've got one side as well. That side is 8. Alright, so what could I do? Well, I don't seem to have enough sides, so I've only got one side. So I'm going to have to see if this rule here applies, the AAA test. This angle here, this angle is in common, isn't it? This triangle, this smaller triangle, has that angle. And the larger triangle also has that angle. They share that same angle there. It's in common. So that must be the same in both triangles. I've also got these arrows here, which are very important. These arrows here mean that the two lines, BC and DE, they are parallel. And there's something very special about parallel lines, or lines that cut through parallel lines, and that's to do with the angles in here. I wonder if you remember this. These two here, These are the same angle. They are corresponding angles. That doesn't look right, does it? Corresponding, I'll just fix that up. That's better. Corresponding angles in parallel lines. So you might remember this as an F angle from last year. So these two must be the same. Now have a look. Do we have enough information now? The smaller triangle and we've got the larger triangle. We do have enough. We've got two of the angles. Therefore, the last one must be the same as well. So let's prove this now. What I need to do is make a statement about these angles being the same and say my reasons for that. So first of all, I'll start off with angle DAE. So this one down here that I coloured in the green, DAE. That's equal to angle BAC, matching up the same order of the vertices. That angle is common to both triangles, so it's got to be the same. I'll now talk about this angle here being the same and give my reason. So I'm going to call this angle DEA. That's equal to angle BCA. And what's my reason? They are corresponding. Ran out of room. I now have two angles the same. The third one is obviously the same as well, just like the first example. So now I'm going to make my statement. Triangle ADE is similar to triangle ABC. So ADE, ABC. Remember to match them up. And my reason is all three angles are the same. So this is really, really handy to know, to recall from last year. Those corresponding angles, this might come up a few times, especially when you've got these two triangles, one inside another one, and you see these parallel lines here. It's giving you a clue that you've probably got in here some corresponding angles. Let's have a look at the last one, a trickier one. First of all, are these two triangles similar? And secondly, can we find the value of x? So let's concentrate on the first question. Are the two triangles similar? Well, I can see that both of them have a right angle. So that's one angle that is the same in both triangles. I can also see that this triangle here has got an angle on the end there, and this triangle, the larger one, actually shares that angle. They both have that angle. So this is another case where we have an angle that is common to both triangles. So yes, they are similar. I've got this angle here in common and they've both got a right angle. So the reason, again, it's AAA. A little bit more challenging is how to find x now. Now that I know that they are similar, I need to set up a ratio. So let's start with the two sides that I've been given, because as you can see, I can't compare these last two sides yet because this x is unknown. So let's look at this side here, the 8 and the 6. We'll set up the ratio. If these are similar, it must be equal to the ratio of the other pair of sides. X over 8. Okay, 8 over 6 must be equal to x over 8. Now what we need to do is solve here for x. So what I would do here is multiply both sides by 8 here. See how x is being divided by 8? Let's multiply both sides by 8. Next step. Do 8 times 8. And now let's simplify this. Now, if you say are using a calculator, you could simplify this further, or you could sort of round it, I should say, into a decimal. But because I've actually simplified this into its smallest fraction, most simplified fraction, I should say, I'm actually going to leave it like this. 32 over 3 is my final answer. So this one is a little bit trickier because I guess it is hard when you've got here one triangle inside the other. Sometimes it can be difficult to visualize it, and also just setting up the ratio as well, making sure that we go, all right, this triangle over that one, and then the x over the 8. We don't want to be mixing these up. The order is very, very important. If you've got one triangle that's sitting on the top of your ratio, that should stay on the top for both of them. Okay. Pause wherever you wish if you'd like to jot these examples down. Thank you very much for watching this video, and we'll see you next time in class.